So today, none of this today will be on the midterm on Friday, so don't worry. But of course, one of the concepts that we discuss, compactness, is on the midterm. So many of the things that we will discuss today will be related to Friday. So main topics is continuity and compactness. Both of these notions we have defined. This lecture is specifically about connecting these more strongly to each other. I mean, they're already connected somehow, but we will discuss specific results that relate in that vein. And so a rough outline of what we'll do, there'll be two parts, so 1 and 2 of this lecture. In part 1, we talk about what do continuous functions do to compact sets, and we'll lead up to that with a motivation. Then we'll use that a little bit. We'll state a theorem to answer that, and we'll prove that, and then discuss a little bit how that theorem can be used to get extreme value theorem. Now, in part 2, we will then talk about the real interest is talking about product sets, but then to get there, we have this. I introduced this concept called the distance between sets, so that we can analyze it a little bit, go through some examples, and then state some theorems involving products of sets. So it gives us a context and a reason to actually be talking about them. These products of sets, they are useful for other things as well, but I don't want to get to them, and I don't think we will have time today. You can use them to conveniently prove in a very short space that products, additions, and divisions are continuous, but the tools for that will be developed today, but we will discuss that in more detail next week. So, okay. So let's start with this first part. What do continuous functions do? Just first to sets. What happens to sets? And there are different directions that one could take this. So let's fix a continuous function, x to y. Now there are some facts. If we take a set in the image, y, and we take its pre-image, then we can say a lot of things. And these are always true, without assumptions. So if you have an open set, V, then the pre-image of it is also open. If you have a closed set of Y, then the pre-image is closed. So this is all the points X such that f of X is in V. So if we go backwards, we get open and closed sets. So things work out nicely. Great. The question that motivates this discussion a little bit is, do these hold the other way around? I mean, often you'd actually want to apply these the opposite way. Unfortunately, you have to be super careful. Sometimes they hold, sometimes not. So we'll go over some bad examples when they don't hold. This doesn't mean that they don't ever hold, but in these particular examples, they don't fail to hold. So let's first look at the open set case. So suppose we have an open set of X, and we still have our function f from X to Y, which is continuous. This was actually asked on Campus Wire. And the question is the image set, so all the values that you attain in the set V, is this open? So this is all the Y's such that there exists an X in V such that f of X is equal to Y. Well, it turns out that the answer to this is no. It seems plausible, but be careful. The set, it's going the other way. So an example, it's pretty simple, is f of X is equal to X squared. It goes from R to R. It is certainly continuous, 131A stuff. Now, V is the open interval -1 to 1, so an open set. If you take f of V, so all the values, then what you get is 0 to 1, which certainly is not open. It's not even closed, so it's nothing, not open. Okay, so the images of open sets can fail to be open even for the simplest of functions. So you have to definitely be careful of that. Same thing for closed sets, except that this time it's much more subtle how it fails. If you have a closed subset of X, then you could ask, does the image have to be closed? But again, the answer is no. So the answer is no here. The answer is no here as well. And the examples have to be a little bit more complicated, and we'll see why this has to be a little bit more complicated, but still relatively simple functions. E to the minus x squared, something you see in statistics a lot. It's a function from R to R. This is certainly a continuous function, composition of continuous functions. Now, if you look at F is the entire space, then this set is closed because it's the full space. And if you look at the image, well, it's best understood by drawing a picture, although that's of course not a fully rigorous proof. It's this bell-shaped function. The range of the function is the open interval 0, half open interval from 0 to 1. Specifically, 0 is not included because you approach it at infinity. And this is the source of the problem, is that if you think that how to prove this, you'll end up with an issue. So not open, not closed. So we'll see this kind of argument later, in the correct sense. So, let's see what goes wrong if you try to prove this. Many people might instinctively think that this is true. It's easy to try to write a fake proof of this. So fake proof, it means the wrong proof. So you might try to something like this. Let yn, we want to show that the image is closed, so let's take a sequence in it, in fv, and that converges to some point y in f. We want to show that y is still in the image of f. Okay, so then we find a sequence in xn in f so that f of xn is equal to yn. Well, this is possible because it's the image set. Well, then we say that, okay, this is a sequence in f is closed, so there exists an x such that the sequence converges to it. And by continuity, limit n it goes to infinity of f of xn equals f of x equals y. So now y is equal to f of x, and x is in E, so y is in F. So y lies in the image set. This is not a proof. So what did I do wrong here? You can either suggest in the chat or unmute yourself. Where is there a mistake? As we saw counterexamples where this proof cannot be true, but where am I saying nonsense? So either in the chat or you can unmute yourself, or I'll wait a small amount of time for you to think at least. And if I don't hear, then I will give an answer. But so in this proof, where I'm making a mistake is here. Everything else makes sense. I'm using continuity right. I'm using the definitions correctly, but there's no reason this sequence that you thus construct, it doesn't have to converge. And it's wrong to say that if you have a sequence in a closed space that it converges. There's nothing like that. If it converges, it stays inside the set, but you can't say that. There's nothing in the problem saying that this sequence xn on the domain side converges. And that's the source where this whole proof crucially fails. We don't know that there is an x. So, but we would like to make this proof work. So we want to fix it, we at least want to find a convergent subsequence. And so this is often a case when you can't, something doesn't have to converge, but sometimes if you can make a subsequence converge, that's good enough. So the correct form of this statement, so openness is not preserved, closedness is not preserved, but what is preserved is being compact. So if you have a compact subset of X, if you have a continuous function, then the image set of a compact set is compact. So this statement is correct, and its proof now looks a lot very similar. So first, well, we want to, what are we showing? We have to state the definition of what, so to help us focus. So we want to show that the image is compact. That means by definition that every sequence for all yn in f of k, there exists a subsequence y and k such that limit as k goes to infinity of y and k converges to some y, so for some y in f of k. And the limit should be in the set. Yeah. Okay. So we're proving this. This proof has a few steps. There's a setup stage. There is the idea of how do we convert it to the compactness of k. So we have to find a sequence in k that corresponds to that. Then we have to apply the compactness of k, and then we use that to get our convergence subsequence and verify that everything works. So our setup opens up this for every quantifier. So fix any sequence yn in f of k. Now, what I mean by lifting? So each yn is inside f of k. So there exists an xn in k. For each yn, there exists a different xn, and that's why we introduced this index, so that f of xn is equal to yn. So this constructs a sequence in k. Now, we have to apply the compactness somewhere, but now that we have a sequence in k, that puts us in a good place. So since k is compact, there exists a convergent subsequence of the xn k. That is, limit as k goes to infinity of x and k is equal to some x. So this is using the compactness of k. Okay, so we get now that a subsequence converges. Now, if you had to guess what subsequence would you use on the y side, the same one. Now, use the same subsequence on the image side and define y is equal to f of x, because, well, this sequence is converging to x, so y is in f of x equals f of x, so, well, since x is in k, y is in f of k. Okay, so that's one thing to check. The limit point is in the set that we're claiming. Now, limit as k goes to infinity, x and k is equal to x. So by continuity of f, we know that limit as k goes to infinity of y and k is equal to limit as k goes to infinity of the same sequence, because y and k right, is the same thing as f of x and k. By continuity, this is, we can pass the limit inside, take f of x, but this is exactly y. So y and k converges, and we found the desired subsequence. Any questions on anything so far? So fairly direct, but you have to be careful. So open and closed sets are not preserved, but compact sets are, and they're the proof that it sort of writes itself in a sense. So that ends that proof. Now, okay, we have a theorem. Great. Let's give some application. Why would you care? So there are two reasons why you would care about this fact. One is extreme value theorem. So we saw a proof of it. That's my preferred proof with the sequences. Here is another proof. It doesn't hurt to have more than one proof of a fact. And it is a fairly short proof, so it gives a different perspective for the same fact. And sometimes this different perspective can be helpful. So suppose you have what is extreme value theorem, a simplified version of it. You have a compact set, you have a continuous function, and you want to say that this function attains its maximum. Well, by what we just said, let's apply that. So since K is compact, we know that the image set is compact. So the image set F is closed and bounded. Let's say this set is non-empty as well, so that we don't have to deal with closed, bounded, and non-empty. Well, by what you did in your homework, since it is closed, well, since it is bounded and non-empty, soup exists. And since it is closed, by what you showed in your first homework, soup is actually in the set. Okay, so soup is in the set, but what does it mean for soup to be in the set? That means that there exists a point in F, so there exists an f of x, so an x, so there exists, in other words, some x in K, such that f of x is equal to the soup of F, because this is the element y that's equal to the soup. And what is soup of F? Well, soup is the value, supremum of the range. It's exactly the same thing as taking the supremum over all the points of K of f of y. So these are the same things. And this is exactly what it means to attain your maximum. There's a point which attains the supremum. Any questions? So image is compact, supremum is in there, it's attained by a fixed value. Done. Much shorter than the sequential proof because it hides it in this other fact. So another way of looking at it and applying this. Now, another thing that compactness does for you, it helps with inverse functions. And in the motivation, I discussed that in 131A, you had a statement about that if you have an increasing continuous function, then its inverse is also continuous, but its proof is kind of annoying in the real case. So this is a generalization of it and actually has a very short proof, at least if you allow for some abstract principles. So, well, to talk about inverses, we have to recall some terminology. This is probably quite familiar to you. So again, our standing assumption is f x to y is continuous. Well, these definitions don't depend on it. So, well, we have a function is 1-to-1. If for every value in the image, there is exactly any value in the range, there is exactly one value in the domain that attains it. So a picture would be X is this 3-point set, Y is, say, this 4-point set, and every point is mapped to 1, and there is no situation where 2 different points of X gets mapped to the same thing. That's what 1-to-1 means. Surjective means that, well, everything in the range has something going to it, but possibly many values will go to the same thing. And if these both happen at the same time, you're 1-to-1 and onto. So bijective, meaning that every value has exactly one value X that leads to it. But because if there's only one value leading to it, then you always have an inverse map, meaning, and it's defined by solving the equation. So f inverse of y is the x such that f of x is equal to y. I mean, some of this you've already learned in high school, so I don't think I need to emphasize this point too much, but this is recalling the abstract terms. Now, the problem that we have to discuss is that if f from x to y is continuous, even if it's bijective and continuous, well, f inverse is defined, but it may fail to be continuous. And this is kind of an annoying thing. I mean, if you've studied algebra or many other subjects, there are many cases in mathematics where the inverse function is just as good as the original function. But in terms of continuity, so metric spaces, topology, R class, inverse functions can be much worse than the original function. And I mean, just to give a sense of it, this doesn't really break continuity. I mean, if you have x squared, its inverse function is square root of x. I mean, say it's thought of as a function on the non-negative real numbers. Well, both of these are continuous, but one of them is worse than the other because square root of x is not differentiable, whereas x squared is differentiable. So in analysis, inverse functions can be worse than the function itself. And this is the problem. But what saves you is if the domain is compact. So compactness again comes to the rescue. So if K is compact, and if you have a continuous function on that compact set, or in this case, it's the whole space, continuous function that is bijective, so it has an inverse, then that inverse will automatically be continuous. So to give an example where this fails, and I won't justify this, but to show that you actually do have to be careful, this is a quite familiar function. So on the domain side, you have the half open interval, 0 to 2 pi, and then you map it to sine and cosine. Okay, we haven't defined those rigorously in this class, but you know what they are. So this function, what it will do, it will map every point here to the unit circle, and it will map it so that actually every point of the unit circle is obtained only once. So say we start at this point, and then we wrap it around, and well, we don't include the other endpoint, so we're not really gluing it together. It just falls an infinitesimally small amount short of the 2 pi length. But this is 1-to-1. Every point here has a unique pre-image. The only point you might worry as having 2 is this boundary point, but it's only mapped from 0, not from 2 pi. So, I mean, now I haven't proven that these are actually not the same. I mean, that this inverse is not continuous. I did not show that, but in a sense, you can think that there's a discontinuity here if you go the other way, because on the top half, you go close to 0. On the bottom half, you go close to 2 pi. So continuity fails for the inverse. So again, something natural, the continuity of the inverse, you have to be careful about. But if you have a compact space, things work out nicely. And again, the proof is actually fairly short if you know what properties to apply. You could do this proof directly from the definition. I would not recommend it because it's actually fairly technical to do. But if you have f inverse y to k, this is defined. Only thing we have to show it is continuous, and we have a theorem that we can use that's particularly well suited to this problem. Namely, by the theorem, this function is continuous if and only if we take any closed set in the image. In this case, these are closed sets in K, that the pre-image under this function, but that is the pre-image of the pre-image of f, which is the same as the image of f. That's a little bit can be confusing, and if you go think what is the inverse of the inverse, you can see that this is the case. Then the fact that you're continuous is equivalent that this set, which is now equal to f of f, the image set, is closed. And this is exactly going back to what we started the lecture with, that closed sets need not be closed. Images of closed sets need not be closed. But what would help us now? Do we have something? We have the compactness of K. So do we know something more about F? Is the question. So, okay, well, our setup is, so we want to verify the condition. Okay, let's fix a closed subset of K. We have to use the compactness somehow. Well, how we use it is we want to go back to our previous theorem that images of compact sets are compact. So K is compact and F is a subset of K is closed. So a closed subset of compact space itself is compact by theorem. Okay. I mean, this is a kind of theorem that you should know actually on Friday. So a closed subset of a compact space is compact. Okay, so we are almost done now. So now if we know that F is compact, so since F is compact and F is continuous, by above, F of F is compact. The image set is compact. But we want the image set to be closed, not just compact. Well, there's a theorem exactly saying that as well. So since F of K is compact, then F of F, sorry, capital F. Then F of capital F is also closed by a theorem from last week. And that ends that proof. So this is a convenient way of showing that the inverse function is continuous, this statement. And the proof uses this characterization of pre-images of closed sets, and the pre-images of the inverse turn into images of the original function, and their everything kind of falls into place. Images of compact sets are compact sets are closed. We're good. Any questions? I know this is a bit fast, probably, but the main thing you should take out, say, from this discussion above, is that images of compact sets are compact, and that there are these applications that you can review later.